Okay, we're going to get started now. Our speaker today is Percy Young, and probably most of you have heard him speak or read something by him before. He has a lot of highly cited papers. He's an associate professor at Stanford, and he has won awards such as the Presidential Early Career Award and the HKI Computers and Thought Award. And we're really happy to have him speaking here today. And as usual, we're grateful to all our speakers who are willing to talk to us, even though they don't get a trip to Pittsburgh and a nice dinner. And we're very grateful for everyone who's speaking with us. So Percy, go ahead.
Thanks, Lori, for the introduction and also inviting me to come. It's actually, I haven't been out to Pittsburgh since 2013, according to my records. So I'm actually glad I'm able to come out here virtually, which is actually a lot easier than flying all the way over there. So thanks everyone for coming to the talk. This talk is a brand new talk. Literally, I finished making it this morning. So it represents a lot of the most recent and somewhat raw thoughts that my students and I have been thinking of. And this is joint work with a lot of students and collaborators. I'll name them Pang Wei, Tao, Yuxian, Steve, Emma, Bean, Lisa, Nelson, Tony, and Robin. And at least some of them I know are on the call, so they can feel free to jump in or if you have questions, put it in the chat, and I'm sure they can answer them. So let's begin. So let me start with a quick refresher on deep learning. So this is the way it works. You typically have a very large and powerful model. And if you feed this model tons of data, then you can get it to do amazing things. And that's basically it. So in particular, one example is imagine you're trying to take x-rays of knees and try to predict whether there's the severity of arthritis. And so people have used deep learning methods to do this. But what happens if the model says there's no arthritis and the doctor says, well, actually, I don't quite agree. Why do you think that is the case? And well, of course, it's really hard to get the model to actually answer. And more generally, how do you interpret what models are doing and intervene and have a more general dialogue about the predictions? Here's another example. So we've seen a lot of impressive results from large language models like GPT-2 and GPT-3 and so on. And they produce stunningly fluent text. But they're prone to not always tell the truth. I think of them as kind of truthy. And what we'd like to do is be able to control the generation and generate text which is based on facts. So in other words, how can we steer language model based on facts? So now taking a step back, there's been a flurry of work. It's kind of shocking how much progress there has been in the last just 4 years or so. Lots of models and architectures, lots of innovation. And because the field is so empirical, a lot of this progress is driven by data sets. So it might be natural to ask, what is it about data sets that is causing this progress? And in particular, for new data set that are coming out, how can the designers pay attention to these things? So this is a very kind of broad and open question. And this is more going to be, we'll have one project that kind of touches on this in a very, is a first step kind of way. Okay, so this talk is going to be broken up in 3 parts. I'm going to talk about concept bottleneck network models for interpretability, prefix tuning for text generation, and then introduce this notion of dataset concurrence. So if there's any questions during the talk, feel free to interrupt. Maybe I'll pause for momentarily to see if there's any questions so far. Okay, so let's jump into concept bottleneck models. So this was based on an ICML paper from last year with Pang Wei, Tao, Yuxian, and Steve, Emma, and Bean. So let's go back to this arthritis prediction problem. So you have an input image and you want a model that predicts arthritis. So you want to understand why is this model making this particular prediction. And it's kind of a black box. So there are ways you can go and do probing or any other kind of post hoc interpretability methods. This is kind of like reading, the brain waves, so to speak. And we'll show kind of how there's some kind of problems with this. But the kind of a gold standard in some ways is a human. So a human, if asked the question, why do you think there's no arthritis? She might say, it's because I don't see any bone spurs, which is kind of extra bone growth in the image. And the doctor might come back and say, well, isn't this thing over here a bone spur? And then the model or say the human could say, oh, okay, actually that makes sense. Now, based on that new information, I agree there's arthritis now. So you can see that what's going on here is kind of an intervention at test time. The model's already trained, and someone can externally influence the predictions by saying, if a high-level concept were this new value, what would the prediction be? And because humans have language and they can interact with these high-level concepts through language, this type of interaction is possible, whereas if you just had a black box model, you couldn't, there's no hooks on it to be able to actually even intervene at that high of a level. So there's a lot of work on post hoc explanations, which are you train a standard model and then you look at the internals and see if you can read out high-level concepts or even design different model architectures to encourage more representable, interpretable representations. And this is obviously connected to this large literature on probing in NLP, where you train, again, these large models and you try to read out. And this style of work is nice because you're dealing with these models which are so highly optimized for accuracy. So people want to use them. So the models are expressive. But like I said before, there's no causal hooks or into the model. There's no way you can really kind of poke at it. So what are we going to do about this? So let's kind of revisit this old idea. Before deep learning, about 10 years ago, it seems like a lifetime, people were interested in building up models that looked at, in computer vision, they were attributes. Maybe in NLP is kind of like reminiscent of good old feature engineering with parse trees and parse speech tags. People would create these intermediate representations and predict those and then use those to predict the final label. And of course, what happened with deep learning was we realized that while these might be more interpretable, they're not as accurate. So these kind of fell out of favor. So what we're going to try to do is take a look at these type of models again, and see if we can kind of resuscitate them using some kind of more modern kind of deep learning ideas. So what we're proposing is concept bottleneck models. And the idea is kind of very, very simple. And it's you take any deep learning network, like a ResNet, and then you take one of the intermediate layers and you resize it to be the number of high-level concepts that you care about. So now the model has two parts. There's an input to the concepts, X to C, and then there's another layer that goes from C to YN, which is usually linear or something more simple. So we can do this for predicting arthritis. You can also, we also looked at another data set, which is given an image of a bird, predict which species of that bird that is. And the concepts here are wing color and beak length and so on and so forth. So, so the idea here is that with a concept about model networks, it's crucial that these concepts are a bottleneck. So when the model makes a prediction, you know that the only information that's going to Y is through C. And that gives you kind of some sort of constructive guarantee that the model isn't really cheating and using some part of the image to predict Y and just giving you some sort of made up post hoc explanation. So how do you train such a model? So we're assuming at training time, we have triples of X, C, and Y. And there are many ways to do this, and which will have some impact, which I'll explain later. So the first thing you can imagine is you're going to train both components separately, independently. So you train using the XC pairs, you train X to C, and then using the C to Y pairs, you train C to Y. So this is called independent training. You can also do things sequentially, where you first train X to C, and now the problem with the independent is that at test time, you don't have concepts at test time. You have to predict them, right? So to kind of minimize the distribution shift, you can take the actual predictions of X to C model and use them as inputs to train the C to Y part, where now the inputs are kind of the predicted inputs as predicted concepts as opposed to true concepts. We can also do joint training. So this is something that's, I think, interesting. So you can write down this objective function, which includes a X to C part and the predicted concepts to the Y part. And you have a lambda factor that governs how much you want to pay attention to the concepts. And if lambda goes to infinity, then you get something more like sequential, where you're first paying attention to making sure the concepts are good, and then you focus on making the predictions are, given those concepts are good. And now finally,
hang on, Percy, there are some questions in the chat.
All right, thanks for the questions. So let's go on. So you can do this joint training, which you train everything completely. So we're trying to get some sort of end-to-end flavor. This is what I meant before, where we're taking the old ideas and then trying to infuse it a little bit with this kind of modern deep learning, end-to-end things that we know to be effective in practice. And then there's a standard training, which is that you have the same architecture, but remember, C is just a layer which if you don't attach any semantics to it, it's just hidden units. So we're just going to train end-to-end from X to Y. Okay, so how do these methods do? So we look at all of these different methods on both the X-ray dataset and the BIRDS dataset. So first of all, let's look at how well the end-to-end performance works on X-ray. So you can see that basically everything is pretty much the same here. So by enforcing this concept bottleneck layer, you don't actually lose accuracy for X-rays. And for concepts, you get, I guess RMSE maybe is hard to interpret, but you get some sort of extra interpretability because now you have these concepts there. For BIRDS, there's a little bit more distinguishing. First of all, if you train independently X to C and X to C to Y, we observe quite a bit of a performance hit, 24% error instead of 18%. And this is kind of the reason that these models aren't that used, because they're just not as performant. But if you look at the joint training, we actually recuperate a large fraction of that gap. So now joint training kind of gives you the best of both worlds in a sense, because you get kind of high accuracy, but if you notice the concept accuracy, how accurate you're predicting the concept, which is some sort of surrogate for interpretability, it actually you don't lose anything from the independent. So looks pretty good. So you can do joint training and you get reasonable accuracies on the end task, but you also get some interpretability. So there's a slight asterisk to this, which I'll come back to in a bit. So now just to revisit the idea of using post hoc explanation. So here you're training a standard model, and then you take one of the hidden units, and then you try to use probing. So you train a linear regressor or a classifier to predict the various concepts. And you see that the accuracies or the error rates are much higher than if you did use a concept bottleneck network. So, and this is not surprising because these models have supervision, and these models don't have supervision during the actual end-to-end training. But this is also just kind of reaffirming the fact that there's no kind of magic mind reading. Like if you train an end-to-end network X to Y, it's going to pick up on spurious correlations. It's going to predict things in a different way than you might want. And if you really care that the model follows a particular mechanism for doing predictions, then it is essential to add this kind of concept bottleneck layer in. One of the nice promises of concept bottleneck networks is that they're more interpretable, and which means that they're kind of maybe more likely to make predictions in the right way. So here's a kind of a simple experiment to test this out. So we had the birds data set where we put the birds on different training backgrounds as test backgrounds. So each species was on, in the forest at a training time, and now it's hanging out in coffee shops at test time. So if you use concept bottleneck models, you actually get much lower error than if you use kind of the standard training, which means that at least in this particular synthetic shift, it's more robust. And more generally, the intuition here is that the concepts are less prone to shift. If the concepts are less prone to shift, then concept bottleneck networks will protect you from domain shift better. I noticed that there is a question from a causal perspective: shouldn't C to X to Y maybe as C as a confounder? Yeah, so this is a good question. It's very tempting to kind of think about this through the lens of causality, and in some ways you can think about, but you have to we have to keep in mind that this is not a causal model of the world. And sometimes it could be anti-causal, sometimes it could be causal, but we're not making any sort of statement about what the world is like. When we talk about interventions, we can think about, I guess the word intervention has a strong causal connotation. And there you can treat this network, if you treat the network as the world, then you can kind of think about causality in terms of the network, if that makes, maybe this will make more sense later. Yeah, but you're right in some sense. If you look at in this particular setting, there is the bird or the knee in the real world, and there's a bunch of these kind of concepts, and that gives rise to the X-ray machine. That, well, I mean, the actual knee gives rise to the X-ray machine, and maybe these are kind of read off that concept. But it's a little bit more complicated because some of these are also not fundamental physical universal quantities. They're kind of guidance provided by doctors that say, oh, okay, if you see this kind of thing, it's it's considered a bone spur. So it's the causality question gets a little bit kind of murky. So we're kind of steering clear of it for now. Okay, so let's go to test time intervention. So remember, we wanted so what good is having this concept bottleneck network model? And one of the really, I think, important takeaways this is that it allows you to have hooks into the model, right? So if the model predicts no arthritis, then you look at the concept bottleneck layer and you say, look at the component that corresponds to bone spurs. And if it's low, that means the model doesn't think there's a bone spur there. But this also means that the doctor can come and say, well, I actually think, I disagree. I think there's a bone spur here. And you can just flip that to a 1. And now you can use this modified concept bottleneck layer to make the prediction. And here it's important that it be a bottleneck because otherwise there might be information leaking from the image to the prediction directly. Whereas if there's a bottleneck, then you know that this is kind of a sufficient statistic for prediction. So we did a kind of experiment to see to simulate what it would be like for a real doctor kind of intervene. So we start with, remember at test time, there's no concepts given. But so the model just makes a prediction, C hat, and then we iteratively choose concepts one at a time, and imagine like an Oracle doctor replacing it with a ground truth. And we're seeing how, if the error kind of goes down as these concepts are replaced. So if you look at the standard model without any concepts, so there's no semantics assigned to the concept bottleneck layer, then obviously this doesn't do anything. And you can see, first of all, that all the concept bottleneck models, as you intervene, you can actually meaningfully make the test error go down by these test time interventions, which kind of is reassuring because that means kind of a doctor in a real setting can come and help the model to correct for some of its mistakes. One thing I'll also point out, which I alluded to earlier, was that there now is a gap between the independent training and these kind of more joint settings. And this is, so remember the independent model is the C to Y layer is trained on gold concepts. And what is happening is that when your doctor is making these interventions, they're replacing the predicted concept with gold concepts. So in some sense, the independent model is more accustomed to gold concepts, and therefore the interventions will be more likely to help it than the joint training. So here you can see that while before, all of these methods were kind of, well, joint training was winning both in terms of concept accuracy and end accuracy. It does actually is a little bit inferior to the independent training through the lens of test time intervention. So the story is between this trade-off between accuracy and interpretability is a little bit more nuanced. General question, is there a connection between this concept, bottleneck networks, and capsule networks? Capsule networks tries to find high-level features on its own rather than defining them manually. So capsule networks, I guess I would categorize them in a class of deep neural networks in general, where the promise of end-to-end training is that the hidden units capture these latent concepts which are useful for prediction. And this, I mean, works well, but as I mentioned before, has the problem that some of these concepts that are automatically learned might be based on spurious correlations that you don't really want. Okay, so to summarize this section, we show that concept of bottleneck words. Just take your favorite network, resize the intermediate layer and train them to match concepts. Obtains comparable accuracy to standard models. What I think is the most important part is it provides constructive explanations, not post hoc explanations. And this allows you to do things like test time interventions. There's some open questions here, right? I think so far we've showed this concept bottleneck models to be effective for these two tasks. And for some things like, let's say, face recognition, maybe it doesn't make sense because the prediction of what is a face, maybe not, or identification of a face, you can't really say, well, what are these high-level concepts? It's kind of more of a reflex. And the natural question that I always get is that, well, you could relax the bottleneck assumption to allow for more predictive accuracy, but you really have to be careful because if you allow a shortcut from X to Y, then the guarantees about explainability become sacrificed. So how to best balance these two things is still kind of an open question. So now I'm going to switch gears to talk about prefix tuning. So this is work with Lisa, who I think is on the call. And so we're talking about text generation. And suppose we wanted to do table to text, which means you're given a structured set of facts and you want to generate some English description of those facts. And given the rise of all these large language models, the kind of the default thing you do is you download the largest language model you can find, and then you fine tune it on examples of your task. So this is great. One downside is that these large language models have a lot of parameters. GPT-2 has 1.5 billion parameters. And imagine you were trying to do this for a bunch of tasks, table to text, summarization, translation. You would have to store an independent copy of your parameters, which is undesirable. So there are some works that try to make progress on this front. So the natural thing you can do is just tune the top two layers. You freeze the remainder of the network and tune only the top two layers. And if you do that, you can tune 20% of the parameters, but you lose accuracy, as we'll show later. You can do what is called adapter tuning, which is this nice idea where you basically have a language model and you add these kind of adapter modules that kind of augment the model at all these different kind of layers. And this you can actually, as we'll show later, get comparable performance. And you can you tune only 3% of the total parameters. So 3% of 1.5 billion that you need to store in addition to the pre-trained LM. So that's pretty good. So now let's ask the question, can we reduce the number of tunable parameters even more? So 3% is of, a large model is still a lot, especially if you're talking about, let's say, GPT-3. So here is speaking of GPT-3, here's the extreme. So GPT-3 offers a kind of a glimmer of hope in a certain direction. So in-context learning is this really cool feature of GPT-3 where you, instead of tuning or fine-tuning the model, you condition on a prompt. And the prompt usually contains an instruction, maybe 0 or more examples of input-output pairs, and an input, and these are just concatenated, and that's the context that GPT-3 conditions on, and you ask it to spit out words, and it might spit out the right answer if you're lucky. And so this is great. The downside is that you can only train on a few examples. So it's great for few-shot learning, and to the extent that your task only demands a few examples, that's great, but often for more complicated things like summarization, you really can't do that well from just a few examples. And GPT-3 is just ginormous. So and in-context learning doesn't really work at all for GPT-2. So, but we can take some inspiration here. And the inspiration is the idea of prompting, which also shows up in a number of different, starting to show up in a number of different contexts. And the idea is that suppose you want to map input to output. What we're going to do is design a prefix so that if you prompt the language model with this prefix and the input and ask it to just complete the next word, you magically get the output out. And so in this case, if the task is to predict the capital from a country, then the prefix you will want is the capital of. And that makes a lot of sense. But what happens if you want to solve the table to text problem? Now the input might be a structured table, so we're going to linearize it into a sequence, and now we're going to ask it, we're going to design a prefix, and here it's not really clear what you're going to do. Maybe you'd say describe or summarize a table or something, and you would like it to output the correct generation, but this is often pretty hard to do. And one might ask, is a prefix powerful enough? I mean, GPT-3 has shown that it is surprisingly powerful, but if you really want top performing, like accuracy that's competitive with fine tuning, can you really rely on prefixes? And if so, how do you find one? So to draw the kind of analogy, it's like you have this language model sitting there, and you're trying to kind of prompt it with all sorts of treats and trying to get it to do kind of to generate various types of behaviors, which is often can be quite challenging. So autoprompt is one paper, which is I think in the space where they search for a discrete prefix for sentiment classification, and they can optimize a prefix to solve that task. But generation is more complicated, and so it's unclear whether you can actually, and discrete optimization is always makes me a little bit sad. So what are we going to do? Let's kind of introduce a little bit of notation to introduce prefix tuning. So standard fine tuning as follows. You're going to take your input X, which is a sequence, and your input Y, and you're going to concatenate them. Let's call that Z. So a language model, like basically any autoregressive language model, like transformers or even LSTMs, are going to compute a set of activations at each time step, H1, H2, H3. And the recurrence is given by some sort of function that takes possibly all the previous time steps, and then the kind of the new input that you want to encode, and you send it through some box, and that gives you a new set of activations. And the dimensionality of that is the number of layers times the hidden dimension of each layer. So if you're fine-tuning, then you take this model and you just say all the parameters inside this LM are fair game, modify, perform gradient updates on them, and hope for the best. So that's this pink corresponds to that you're tuning the entire model. So here's the idea of prefix tuning. So this slide will describe what prefix tuning is formally. So we can intuitively think about prepending these virtual tokens here. And this is going to act like the prompt or the instructions. But instead of thinking about these as words, we're just going to think about them as arbitrary free parameters. And remember, h is number of layers times the hidden dimension. So theta I is just going to be these free parameters, which is number of layers times the hidden dimension times the prefix length, which in this case is 2. So pictorially, this looks like you're going to optimize this prefix only, and while holding all the parameters of the LM fixed. Okay, so why might this kind of work? Well, the prefix, even though you're kind of only influencing what's happening in the beginning, because of the self-attention mechanism of the transformer, which is you're using the pre-trained LM's kind of mechanism, it's going to attend to the prefix and somehow use it to solve your downstream task. So there's a question, how does one select these virtual tokens as a prefix? So I want to emphasize that these virtual tokens are not actual tokens in the sense that is a token. So mathematically, this is what hopefully the math kind of clear answers the question. They're just going to be vectors that occupy the kind of the entire depth of that network at that time step. And they're the only reason I call them virtual tokens is that you can think from the lens of the transformer that's trying to generate. It still thinks it's a language model because we haven't modified the parameters of language model. So it thinks it's a language model. It's just attending to these things that type check as possibly driven by some real tokens, but they're all just kind of made up tokens. Or not even tokens, they're just made up numbers that are tuned for the downstream task. So we ran this on a bunch of table to text data sets. So one of them is this E2E data set, which you take a structured representation of restaurant review and you want to generate a review. And so let's look at this plot here. So here I'm plotting the percentage of the parameters I'm tuning. So full fine tuning is at 100%. And I'm looking at the blue score here. So full fine tuning is here. And if you fine tune only the top 2 layers, you get a mild drop. So you're actually saving quite a maybe 5x reduction in the number of parameters you have to tune with minor drop in number of parameters. And then with this adapter tuning, which preserves most of the LM parameters but adds these adapter modules, you can see that it actually, you can go down to 3% of the tunable parameters with actually a slight increase in the blue score. But if you start taking the adaptive parameters and you be more aggressive and say, I'm only going to have 0.1% of the tunable parameters, then accuracy starts kind of plummeting, or blue score starts plummeting. Now, with prefix tuning, we're also kind of normalizing for the number of parameters we're touching. So with only 0.1% of the parameters, we actually are able to outperform all of these methods, even fine-tuning with 100% of the parameters. So this, I think, answers your question that it does really matter which parameters you're fine-tuning. You can't just like take a random subset of parameters and tune them. So somehow the inductive bias of preserving part of the LM and fine-tuning another part of the LM is really crucial for getting good trade-off between a number of parameters and accuracy. So here's another data set, WebNLG, the same, maybe I'll go over this relatively quickly, same trends, fine-tuning. Now you're seeing quite a big drop when you do only fine-tune the top 2 layers. And adaptive tuning does a little bit better, but again, if you kind of really starve it of parameters, now it does worse. And now prefix tuning is slightly worse, or maybe comparable to fine tuning, but again, it's only using, I'm only touching 0.1% of the tunable parameters. In Dart, which is another table to text generation data set, which is even more complicated. Now we're seeing a drop in when you fine tune only the top 2 layers. Adaptive tuning is a bit better, but prefix tuning is able to hold comparable results with fine tuning, but only with 0.1% of the parameters. So it seems like you really, in these data sets, don't lose performance at all from just using prefix tuning as opposed to fine tuning. We also played around with summarization. Here we're using BART, and you can read the paper for more details how the idea is it's adapted. You have to insert a prefix both for the encoder and decoder. So on the XSUM data set, fine tuning is here, and prefix tuning does suffer in performance. We can add a bit more parameters to increase the accuracy, but it's still slightly worse than fine tuning. And this is because summarization we think is just a much more complicated task. And so prefix tuning might be kind of hitting its limits of some sort. So one really cool thing that we noticed is ability to extrapolate. So let's say we train a model on particular kind of categories of data, like buildings and sports teams. And we're going to see how well it generalizes to unseen categories like artist. And so the tables, while there are some fields which are uncommon, there are also other commons which are not, like architect only shows up here, whereas now we have to deal with these unknown, never seen before words like genre and derivative. And for this, we looked at fine tuning. So now we're grouping fine tuning methods, which basically just fine tunes the LM more generally, versus these methods which include prefix tuning, but also adapter tuning, which preserves the pre-trained LMs and more augments it. And we noticed that there's a stark contrast. So on this OD setting, the methods that preserve the pre-trained LM are way better than the ones that fine-tune. So this is kind of suggestive that preserving the LM seems really important, especially on out-of-domain examples. So one thing I want to highlight is if you were not doing, is the importance of prefix tuning where you vary the parameters of the entire kind of transformer depth. So one thing you could imagine is you only prefix tune, but modify the embedding layer, and then you just use the LM to kind of fill in the rest. So this is much less expressive, and we see that there's a significant accuracy drop if you only tune the kind of embedding layer. Notice that optimization over a discrete prefix, which is things like what autoprompt does, is even less expressive because that is optimizing over embedding layers where the embedding have to correspond to real words. Whereas here, at least I'm allowed to produce arbitrary vectors, but still that's not good enough. And I think we really need the kind of full expressive power of prefix tuning that touches all the layers to get high accuracy. So notice that now this really makes it so that we're not talking, these virtual tokens are, I mean, really not tokens at all. They're just like kind of a construction that kind of you're jamming it into this transformer so that the LM takes over and just starts using it to magically produce the right output for your given task. So let me summarize this section on prefix tuning. So the key idea is prefix tuning is still a form of lightweight fine tuning in the sense that we're taking an LM and then we're using training data to modify its parameters. So in contrast to things like in-context learning or kind of test time control generation decoding. But the key thing is that it draws inspiration from prompting, or more generally kind of conditioning. The idea that an LM, how do you modify its behavior? Well, you can change its parameters, but you can also change its kind of context that it gets to condition on. And that seems like a very powerful way. And prefix tuning is kind of a way to kind of marry the two together. So the results, I think, are quite nice. We get comparable performance by only tuning 0.1% of the parameters. And it extrapolates better out of domain, which I think is always exciting because we want our models to work well in novel settings. At the same time, there's a lot of open questions. So for example, summarization, we're still not performing as well as fine-tuning, full fine-tuning. Now that's, obviously with only 0.1% of the parameters, so that's kind of a hard thing to compete against, but we were able to do it for table to text. So maybe summarization is just more complicated. Why does prefix tuning work? We suspect that it preserves the LM, but that's kind of just intuition. Can we formalize that a little bit more? And then, of course, I think the main thing is that there's a whole space of lightweight fine-tuning strategies. Which parameters you decide to fine-tune, position carefully where, I think do have quite a big impact on your generalization abilities. So using these kind of insights of preserving the LM and the idea of prompting, maybe we can find something even better than prefix tuning. All right, so maybe I'll pause a moment for questions in case there are any on prefix tuning. So the final section, so dataset concurrence. This is a really weird kind of a project, and I'm going to pose a bunch of questions I think as a community we should think about. I'm also going to provide a bunch of experimental evidence that I'm just going to say up front doesn't answer the actual question, but hopefully gives us some hint at it. So I'm going to suggest an answer, but I want to really caution you in how you interpret these results. Okay, so this is a project with Nelson, Tony, and Robin. So the question is, can small and synthetic benchmarks drive modeling innovation? So we all know that data sets play an extremely important role in NLP today, and also in computer vision AI more broadly. And they allow us to kind of compare models, benchmark it, kind of motivate people to kind of rally around common tasks. And it's fair to say that it kind of led to a bunch of different innovations in modeling. And still, people are pumping out lots of new data sets. But I feel like there's not really much kind of formal guidance on what aspects of a data set are really good. It's basically, here's a data set that captures some new phenomenon. And we want to make sure our baselines don't solve the task. We want to make sure that humans do well. And there you go. And that's kind of the extent. So the question is like, can we say a little bit more? Can we be a little bit more rigorous about this process? So what makes a good data set? That's kind of the overarching question. And there's two conventional pieces of wisdom here that I want to question and challenge a little bit. So the first, that more realistic data sets are better. And this is kind of taken for granted. I think this is kind of, there's a paper that talks about the ecological validity and how, criticizes a lot of benchmarks for language user interfaces for not being realistic, enough. And most NLP data sets, I think, are not that have, modest ecological validity because they're crowdsourced or whatever, and we're not really attached to real users. So I think there's just a general tendency that we, as a community, think like more realistic data sets are better. The more real users they come from, then that's just automatic, automatically good. The second conventional wisdom is bigger is better. And certainly we've thought this ourselves when we're creating Squad. We created a data set of 100,000 questions, which at the time was much larger than anything that existed, which was also kind of somewhat realistic. And I think if you read datasets paper, all of them tout kind of, we collected 1 million of this and 1 million of that. And I think size is one of these things that is not really kind of questioned. And so are these indeed good properties? And before answering this, I think it's really important to clarify something. And it's good for what? And there's two types of things that you might be good for, which I'll call direct improvement and indirect improvement. So direct improvement is when you're trying to improve a system, a real system, for example, something that actually answers questions for you. And here it's undoubtedly the case that more realistic and larger is better. Like you want data that's close to the distribution of questions that a user might ask. And the more data you have, we know that error goes down. So this is kind of not really controversial. But I think when you ask about indirect improvement, which is, does the data really improve the set of modeling approaches that we have? Does it drive modeling innovation, which then can be applied to many different data sets and there cause improvement on direct improvement later down the pipeline? It becomes less clear. And I think there's often a conflation of these two, which leads to us kind of assuming realism and size are kind of just kind of disputable. So I want to challenge this this paper focuses on, let's focus on indirect improvement for now. And just kind of as an anecdote, so LSTMs, at least before transformers, they were kind of the king of NLP, and they were developed on synthetic data. So original LSTM paper, here is the dataset description. It's some sort of there are actually multiple synthetic datasets, but one of the more challenging ones is that you're trying to stress the model's ability to look at kind of hold things in memory for a long period of time. And so, clearly no direct improvement on any task anyone cared about, but obviously drove modeling innovation, LSTM, which then later became the bedrock of many real NLP systems, which were used by many real people in the real world. I think I've said real too many times there. But let's actually take a closer look. So we're going to look at SQUAD. So SQUAD is a question answering data set. You have a passage, you have a question, and the goal is to produce the answer. And throughout the last 4 or 5 years, there's been a lot of different modeling architectures, or modeling approaches, I guess we'll call them, developed for SQUAD. And the question is, did we need SQUAD, or what aspects of SQUAD were useful to drive these modeling innovations? I think SQUAD was, is where some of the first kind of self-attention stuff kind of started surfacing. So, is this SQUAD? Do we need to collect 100,000 crowdsourced examples? So there has been kind of related work, which is different. So I want to contrast. So going back to direct improvement, there's some recent work out of Berkeley that says, let's take a bunch of SQUAD models. So each of these points is a SQUAD model. Let's plot the SQUAD F1 versus the F1 on an out-of-domain test set, which is on New York Times. And what we find here is that there's a strong correlation between in-domain performance and out-of-domain performance across all these SQUAD bench models, I should say systems. So each point here is a system, which is a particular model with parameters. And this is saying that if I had developed better SQUAD models, then if I just take these SQUAD models and put them out to New York Times, then I would get kind of better results. But the question we're interested in is for indirect improvement, and that's different. So instead of taking systems, which are models with parameters, we're going to take modeling approaches, which is an architecture plus training procedure. So we take all of these modeling approaches, and now every dot here is a modeling approach where we take SQUAD, train on SQUAD, and test on SQUAD, and that produces in the x coordinate. and then I'm going to train on UseQA and test on UseQA, and that produces a y coordinate. Okay, so this is saying if we were taking all these modeling approaches and instead of using squad and using UseQA, will we get kind of the same trend? In other words, are modeling approaches on squad, do they transfer to a UseQA? And more formally, we're going to define the notion of concurrence between two data sets as you measure the correlation between accuracy of modeling approaches A on one data set and accuracy on modeling approaches on the other data set. And notice that accuracy here is you take A, you train on the train part of D1, and you test on the test part of test split of D1. Okay, maybe I'll pause a bit. Let's move on. So in the next few slides, I'm going to walk through a bunch of different data sets and measure the concurrence with respect to squad. And we're going to explore different things based on realism and see what is kind of necessary to concur with squad. And I should say that we're using squad as just kind of one example. There's nothing necessarily sacred about squad other than that it's kind of a canonical data set. You could also do the same thing with natural questions or your favorite real question answering data set, and I think the results would be similar. So let's first look at human constructed data sets. So since squads came out, there's been a number of different QA data sets which look at different aspects. So questions that are created without looking at the answer, natural questions kind of boasts questions that are asked by real users who want to know the answer rather than crowd workers. There's ones that require numeric or multi-hop reasoning, and so on. And so each of these plots shows a concurrence plot between, on the x-axis is the accuracy for squad, and on the y-axis is accuracy of any of these respective data sets. And we see that in broad strokes, there's high concurrence. Except for on drop, there's kind of this bimodal effect where the pre-trained meta models and the non-pre-trained models behave a little bit differently. So at the risk of trying to jump to conclusions, this suggests that, at least, let me phrase it differently. At least it doesn't rule out the possibility that squad would somehow, or any of these data sets are somehow special. In the sense that if we had natural questions or UseQA, maybe we would have seen kind of the same progress. And so this is saying that maybe all these kind of differences in the data set, at least from a point of view of model innovation, are, I don't know, it's not clear how important they are. Okay, so now let's try to get a little bit more ridiculous and make this data more synthetic. So let's look at this children's book test data set, which is a closed data set. And so in closed, you take a bunch of raw text and you make up a question answering data set. So you take this text and then you take the last sentence as a question and you blank out one of the words and you ask, oh, what is that word based on the context? So this came out actually in 2016 and has been around for a while. And I think it was often thought of as, well, okay, closed data sets are maybe, they're large, which is nice because they're derived from raw data, but they're not really realistic. And so let's look at the concurrence. So we see that there's actually high concurrence across a number of different closed data sets. Record and CNN are a little bit lower, so it's not perfect. But at least for example, CBT, the concurrence is very high. So now it doesn't, we can't really conclude what is important, but we can kind of say like, well, it's not clear that CBT and squad are fundamentally different as measured by these the models that we have. So now let's give it even more synthetic. So going back to 2015, the baby is kind of this classic archetype of artificial natural language, benchmark for question answering, designed to encourage the model to do a bit more reasoning. And here we see that baby has very low concurrence with squad, which means that if you had baby, then you wouldn't have promoted the same architectural kind of innovations as squad. So this is, I want to stress that concurrence is not necessarily, lack of concurrence is not necessarily bad, right? It's baby does stress a different aspect of modeling that squad doesn't, in particular more reasoning. It's just saying that they were getting at kind of different aspects of a data set, and certainly kind of the open-ended long tail behavior of language squad has and baby doesn't. So now can we create a synthetic data set without using real text that concurs with squad? So at this point, we're kind of just challenging ourselves and trying to really understand what's going on. We already have CBT, right? So you can think, okay, we're done. CBT is kind of free, large, and we can create low closed data sets, and we can continue to drive innovation. But we want to dig into what it is about data sets that's driving concurrence. So here's what we call fuzzy synthetic QA. And we're just going to generate a bunch of random words from a unigram distribution. Absolutely no structure in the passage. And we're going to take a part of the passage and then fuzz it up by essentially kind of quote unquote synonymy, which is basically looking at words in nearest neighbors in glove space, and call that the question, blank out a particular word, and call that the answer. And so this is a pretty awful synthetic data set. It looks nothing like language. So how's the concurrence? It's pretty low on average, which is, I don't know, maybe it's kind of expected. But one thing that's kind of interesting is that if you look at the non-pre-trained models, the concurrence is actually not bad, right? And it's maybe not surprising that it doesn't concur with pre-trained models, because pre-trained models are based on real English. So if it doesn't look like English, these models aren't going to do anything, which is what you see here. But the pre-trained models or non-pre-trained models are more or less about kind of more sophisticated sequence modeling. And this high kind of concurrence on these non-pre-trained models shows that the gains here that you were getting are kind of mirrored by this data set. And that kind of, I don't know, gives you some intuition like what is the nature of the innovations and its ability to kind of deal with these type of fuzzy matching, which we kind of suspected a little bit. Okay, so now the question is, how do we get concurrence on these pre-trained models? So we designed another data set. So we're trying to kind of hold one hand behind our back and say we're not going to use real text. So let's use Wikidata instead. So this is knowledge base of facts, which are triples, entity relation entities. And we're just going to construct the passage by just piling down a bunch of triples. And then we're going to take the question is going to be you're going to take a triple and you're going to fuzz it by these aliases which are given by Wikidata. So for example, the caterer is going to be fuzzed to like the river city, for example. And then there's going to be some hyponyms and inverse relations, some more details which you can read the paper for. So again, this is not natural language at all. It's maybe it has some real words and has some kind of rough structure. Let's see how we concur. So concurrence is actually pretty good. I mean, it's not perfect, and maybe it's not as high as some of the other human data sets, but it's actually kind of, I mean, I found surprisingly good given that this data set is not using any real text. And certainly if you try to publish this data set as a, hey, here's my new data set, people would you'd be laughed out of the room. But yet it still has concurrence, which gives you a little bit external validity for this data set. So another thing we looked at is does size matter? So we subsampled squad to 1K, 10K, 20K examples and measure concurrence with squad. And here we notice that concurrence is pretty good all the way down to 10 or maybe even, or at least 20K and maybe 10K, which means that, again, suggests that maybe if we had squad just be 20,000 examples instead of, 60,000 examples, at least for train, it would have been kind of enough to draw, the modeling innovations. So I'm being a little bit kind of, vague on purpose. So let's try to discuss now what can we actually conclude from this concurrence. Short answer is nothing, and let me tell you why. So the holy grail question is a causal question. Is if I release this data set into the community, would it produce meaningful modeling innovation? That should be kind of the main design. That's the kind of the main question that data set designers should have in their head. But it's ultimately unanswerable. So we can ask a different question, which is a counterfactual question. Would a particular data set have produced the same modeling of innovations as squad? Now, this question is also unanswerable, so because we can't go back in time and undo squad and release the data set and replay history. So we can think about the actual question we're answering in this project as, does a data set concur with squad on squad models? And I want to say that this is a necessary but not sufficient condition for the counterfactual question. So there are some caveats here. There's extrinsic factors. We're purposely looking at intrinsic factors of a data set and seeing, because we're trying to kind of challenge intuitions that people might have. But it's clear that external factors influence things a lot, like how a data set looks and how seemingly realistic and whether it claims to kind of have multi-hop reasoning or something is all factors that influence the development of modeling approaches. And these are not to be diminished. One other caveat is that modeling innovations are not in isolation, especially now with pre-training, right? So we can't really isolate the contribution of a single data set on modeling innovations. So, and finally, this analysis was done on squad models, models which were developed after squad, as opposed to models that were developed on a synthetic data set. And the worry is that, well, the models on the synthetic data set might not show concurrence with the real models on the squad. So that's just a kind of caveat that we have to keep in mind, which are the gaps between the actual question and the counterfactual question. So to summarize, we are introducing this idea of concurrence as a tool to help us ground out some of our intuitions. And it's capturing the extent to which two data sets could drive similar modeling innovations. And I highlight this could because it's really, there's no guarantees of anything here, but it's the best thing that we can do right now. And it gives you something quantitative to look at. And I think we've successfully constructed a small synthetic data set based on Wikidata that concurs well with squad. And the lesson here is that don't judge a data set by its looks, because at least most people I talked to at the time would have guessed that Wikidata synthetic questions would not concur because it's just kind of obviously made up data set, which is very artificial, but yet it does. And so there's a lot of caveats and gaps here, but I think the overall message that you should take away is that I want to spur discussion about what makes a good data set, because I think these data sets are what we kind of are kind of bread and butter in some sense in NLP, and they shape the way that the field evolves. And I think we need a kind of a better and stronger language to have this discussion. Okay, so to wrap up, we talked about 3 different projects, concept bottleneck network, models, where the goal was to be able to design models that provide explanations, but in a constructive rather than post hoc sense. And this enabled us to do test time interventions. We talked about prefix tuning, which was this very efficient way of harnessing otherwise kind of uncontrollable language model and getting it to do kind of controlled generation tasks. And then we looked at dataset concurrence, which is a measure which hopefully sparks more discussion about what makes a good dataset. And so maybe I'll end on one note, which is that we live in a very exciting and interesting time where we have all these large and kind of powerful models. And I think a big challenge kind of for NLP in the next few years is how you harness them appropriately for downstream tasks. And we've suggested kind of via concept bottleneck networks and prefix tuning as just 2 ways of kind of getting at that problem, but I think there's many more to be discovered. There's also issues of kind of bias and toxicity of which are a whole another discussion which I didn't get into, but I think are really interesting. And important themes I want to kind of take away is that we talked about interpretability and controllability. I think these are 2 aspects of kind of a more general question of interaction and how we as either users or model developers interact with our models, both at training time and at test time. One of the things that's exciting about these large pre-trained models is that the conditioning aspect of language model opens up new avenues for thinking about controllability. In particular, like a prime example is in-context learning, but there's, I think, many more things to be discovered. And of course, efficiency, I think, is going to be a major challenge going forward because, with things like GPT-3, you can't even, well, even if we had access to it, I think it would be very, very hard to kind of work with. So I think an important research direction is figuring out ways to be able to get similar or comparable results with being much more resource efficient. So I think there's a lot of interesting questions here, and it's a pretty exciting time to be in NLP. So with that, thanks to all the collaborators and funding agencies again, and I will take any questions.
Great, thank you so much. It's a wonderful talk. I think there are a lot of questions already.